Hi guys, so today is 1.6 inverse functions. Today we're going to take a function and determine if it has an inverse function. We're also going to compare the domain and range of the original function to the inverse function. So getting started, let's just talk about what an inverse relation is. So an inverse relation simply means that if we have an ordered pair, and let's say that that ordered pair is AB, then the inverse relation is going to be BA. All right, if G of X is the inverse of F of X, then we would say G of X equals the inverse of F of X. F inverse of X. The little -1 does not mean it's raised to the power of -1. It's standing for the mass symbol, which is inverse. So this is F inverse of X. Example 1, find the inverse of the ordered pairs. So here are your ordered pairs. The inverse is you're just going to take the A and B and switch it to B and A. So you can see I did that. The original happens to be a function because for every input, there's exactly one output, which means that the inverse is also a function. All right, so inverses have a special property when you graph them. They're going to be symmetric over the line y equals x. And if you remember what y equals x looks like, it's just going to be a line that looks like ooh, little crooked like that. And that's y equals x. So we're going to see symmetry over that diagonal line. Now, horizontal line test is going to tell us if the inverse is a function, because sometimes we have inverses, but they're not functions. So if you take the original function, you're going to perform two tests. The first test on the original function is the vertical line test. The vertical line test is going to tell me that it's a function to begin with. Then the horizontal line test is going to tell me that that function is what's called one-to-one, which means that it will have an inverse function. The definition of one-to-one function. A one-to-one function is a function whose inverse is also a function because the original passes the vertical and the horizontal line tests. So let me show you how you find an inverse and then how you can restrict the domain to have an inverse function. So let's just take the simple quadratic parent function y equals x squared. So y equals x squared, if I pick a couple of values for x, maybe -2, 0, and 2, when I plug them in for x, -2 squared is 4, 0 squared is 0, and 2 squared is 4. And so here's my graph. I have a point at 0, 0. I have a point at 2, up 1, 2, 3, 4, and then a point symmetrical to that at -2, 4. So here is my original quadratic function. And does that function pass the vertical line test? Well, the vertical line test just simply means if I were to draw a vertical line, no matter where I draw that vertical line, it's only going to hit the function in one place. Therefore, does it pass the vertical line test? The answer is yes, absolutely. Now, the horizontal line test means that when I draw a horizontal line, let's see if I can pick a different color. Let's do green. I love green. So when I draw a horizontal line, you can see that it fails the horizontal line test because it's hitting this quadratic function in two places, and the horizontal line test says it can only hit it in one place. So let's answer our questions in this box right here. Does it pass the vertical line test? The answer was yes. Does it pass the horizontal line test? The answer is no. So let's look at what the inverse looks like. The inverse of y equals x squared is not going to be a function because it fails the horizontal line test. So if we take these values here and we switch them, so we take AB and rewrite it as BA, then I have some points that are the inverse relation, not a function. So if I graph those, I have a point at 0, 0. I have a point right 4 and down 2, and a point right 4 and up 2. And you can see when I draw this inverse relation, sorry, it looks bad. You can see that it's going to fail the vertical line test. So if I draw a vertical line, you can see that that vertical line hits it in 2 places, which means this is not a function. So it fails the vertical line test. Let's write that in here. So does the graph pass the vertical line test? The answer is no. Is the graph a function? The answer is no. So the next question is, well, then how can we make it a function? So this is where restricting the domain comes into play. So what we can do is we can take, I'm trying to find a highlighter, we can take the original function and we can just pick part of that original function. So let's just say that I restricted the domain to just this part. That means that my new domain is going to be 0 to infinity, and I'll include the 0. Now, if that's my new domain, then when I come down to the inverse, I'm only going to be using this part of the function. And that means now it passes the vertical line test, which means it is a function. And so this domain, the new domain, is going to be 0 to infinity. All right, let's go over here. The original domain, I didn't write that in, but the original domain was negative infinity to infinity, and the original range was 0 to infinity. And when you take the inverse, the range becomes the new domain. So here, if you look at this graph, even before I restricted the domain was 0 to infinity. And the range, this is going down forever and up forever, so the range is negative infinity to infinity. So something to note about inverses is the domain will now be the inverse's range, and the range will now be the inverse's domain. But this was not a function unless I restricted the original domain to this, and here's my new inverse function because it's only this piece of the graph. So now let's talk about if we have a function and its inverse and we take the composition of the two, it's almost like they just undo each other and we end up getting the identity function, which is y equals x. So what this means is if g of x is the inverse of f of x, then we have f of g of x, which is the composition function, and g of f of x is going to equal x. The domain of f is the range of the inverse, and the range of f is the domain of the inverse. So if I'd asked you to confirm if f of x and g of x are inverses of each other, and we want to confirm that algebraically, then if I find f of g of x is equal to x and g of f of x is equal to x, then I know that the two functions are inverses of each other. So let's look at this together and let's find f of g of x. So I like to start with g of x. G of x is the cubed root of x plus 1. And we're going to put that into function f of x. So we're going to put that into function f of x. So now, if I have f of the cubed root of x plus 1, I would come up to function f, and where I see x, I'm going to put in the cubed root of x plus 1. And that's going to be cubed, subtract 1. And you can see what's going to happen where the cubed root and the cubed are going to cancel each other out. Now I have x plus 1 minus 1. And x plus 1 minus 1 is equal to x. So far, so good. Now, to confirm that f of x and g of x are inverses of each other, I also have to find g of f of x. So this time I'll start with f of x inside, which is x cubed, subtract 1. And I'm going to find g of x cubed minus 1, which is g of f of x. So I come to function g. Here is what function g looks like. And where I see an x, I'm going to put in x cubed minus 1. So this is going to give me the cubed root of x cubed minus 1, x cubed minus 1 plus 1. And then the minus 1 plus 1 are going to cancel. That's going to give me the cubed root of x cubed. And now I'm left with simply x. So since each of these equaled x, f of g of x equaled x and g of f of x equaled x, I just confirmed that f of x and g of x are inverses of one another. So what I'm going to do now is I'm going to find the inverse relation of this function, and then I'm going to state the domain and the range. So the first thing to do is you're going to switch the x and y. So f of x, if I write that as y, is equal to 2x over x subtract 3. So start by switching x and y. So you have 2y over y subtract 3. Now you're going to want to solve for y. So we're going to start. You could just cross multiply if you would like, or you could just multiply both sides by y minus 3. So on the left-hand side, I have x times y subtract 3 is equal to 2y. Let's distribute that x. So now I have x, y subtract 3x is equal to 2y. I'm going to come back up here. So now I want to try to gather all my y's together on the same side. So let's take the 2y and subtract it over to the left. So I have xy subtract 2y is equal to this negative 3x I'm going to add to the right side. So it equals 3x. Now what we're going to do is factor out the y. So I factor out the y and I'm left with x subtract 2 is equal to 3x. Now I can divide both sides by x subtract 2, and I've just found the inverse. So I'm going to take the y and replace it with the inverse notation. So f inverse of x is equal to 3x over x subtract 2. Now what we're going to do is explore the domain and range of this original function, f of x, and the domain and range of the inverse function. So let's go to the next page. And the domain of function f is going to be negative infinity to 3 and 3 to infinity. And what you need to note, if you were to graph this on the graphing calculator, this is what the function and the inverse function look like. The red is the inverse function. And what we notice is the domain of the original becomes the range of the inverse. And the range of the original becomes the domain of the inverse. So that's kind of cool. So this is what it looks like graphically, and you can verify that we have this symmetry over the line y equals x. So now what we're going to do is we are going to confirm algebraically that they are inverses of each other. So we're going to find f of f inverse of x, and then we're going to switch it and find f inverse of f of x. So starting with the first one, f inverse of x was 3x over x subtract 2. We're going to plug that into function f. So here's function f, and everywhere I see an x, I'm going to put in 3x over x minus 2. So this is going to equal 2. Oh, I don't want a highlighter. I want black. All right, so this is going to be 2. And then we're going to put in 3x over x subtract 2. Over, and then here's an x, so we're going to put in 3x over x subtract 2. And then we still have subtract 3. We've got a complex fraction here, so we're going to just go ahead and get rid of all of the denominators. So if we look at all the denominators, we're going to multiply by x subtract 2 over x subtract 2. So in the numerator, the x subtract 2's will cancel, and we're left with 6x. So that's going to equal 6x. And in the denominator, this x subtract 2, you have to multiply to both parts because of the subtraction sign. So x subtract 2 will cancel, leaving me just 3x. Subtract, and then nothing cancels on the second fraction. And so you're going to have to take 3 and multiply it to the x subtract 2, which is a negative 3 times x is a negative 3x, and a negative 3 times a negative 2 is a positive 6. Now I end up with 6x over 6, which equals x. So now I'm going to do the same thing again, but I'm going to confirm that f inverse of f of x is also equal to x. So now that I already took f of f inverse of x, I'm going to switch the order. So I'm going to start with f of x, and f of x up here is 2x over x subtract 3. I'm going to plug that in to function f inverse. So here, this is going to go in every time I see an x. So I begin with 3, and then I see an x, so I plug in 2x over x subtract 3 over, and then I have x subtract 2. In place of x, I put 2x over x subtract 3 subtract 2. Now you're going to see that I have x minus 3 as denominators. So I'm going to multiply this whole complex fraction by x minus 3 over x minus 3. Now the x minus 3's will cancel, leaving me 6x. 3 times 2 is 6x. And then in the denominator, the x minus 3 has to be multiplied to both parts because of the subtraction. So the first part, the x minus 3 cancels with the x minus 3, and I have 2x. So let me put that in, 2x. Here, the, let's see, the negative 2x times x is negative 2x. And then negative 2 times negative 3 is positive 6x. This is looking, or not 6x, positive 6. This is looking great. So now those cancel. 6x over 6 is equal to x. Ta-da! I just confirmed that those two functions are inverses because all of those operations canceled out, leaving me x when I did composition functions. So that's everything. Don't forget to answer the reflection question and submit. Oh, actually, you don't have to submit your notes to Canvas this time. You just have to put them in your math note guide, and we will check them in class. Thanks, everyone.